that because of our normalization, this term right here, which is the left transpose times the right, is just simply equal to 1, right? So I can write, for the sake of conciseness, I'm going to write lambda j prime, which is this, is equal to all this minus that. And that's rho j transpose times a prime times phi j plus cj transpose times a times phi j prime minus phi j transpose phi j prime times lambda j, right? That's the equation up to there. In order to create some room, I guess I could still write one more down. So I guess I'll use one more down. So in this case, what are we going to do is we are going to take this, this and combine the equations. So we'll have lambda j prime is equal to rho j, cj transpose times a prime times phi j plus, and then here we're going to have phi cj transpose common factor of a minus the identity times lambda j, the identity times lambda j, close parentheses, phi j transpose, right? Okay, now I have to erase. Right, so we are there. Now what I want to show is the following. Remember, again, that the eigenvalue problem we had phi j transpose times A is equal to Cj transpose times lambda j, right? That we proved, that we showed is the left side eigenvector eigenvalue problem. From here, it implies that Cj transpose, common factor of A minus the identity times lambda j, is equal to 0, right? Now, from this thing here, we can see that this term is equal to 0 because of this part, right? And therefore, taking that as 0 times phi j prime is 0, we arrive at our final answer with regards to the derivative of the eigenvalue of a matrix with respect to a parameter, which is the following. You take the left eigenvector transpose, you multiply it times the derivative of the matrix, you multiply it by the right eigenvector, and you're done. Okay? That is the derivative. Okay? Quite simple. Once you have the eigenvectors, the right and the left side eigenvectors, you get this. Now, at this point, it's probably worth stopping for just a second and making a commentary. We can always make the norm of the right side eigenvectors whatever we want. We could also do the same on this one, but we cannot make the two norms independent to each other, right? Because we've assumed in our derivation that phi j transpose times phi j is 1. Now, for the sake of argument and for a specificity, let's say that we've decided that we take the norm of the right side eigenvector to be 1. So the question that comes to mind right now is, what makes the derivative of an eigenvalue be large? Well, since this norm is 1, of course, these are matrices and vectors. But loosely speaking, if this norm is 1, and this is just whatever it is, it's clear that as this becomes large, it's because the left side transpose has a norm, or it's a vector that has large entries, right? Okay, now what makes the left side eigenvectors have large entries? Well, for that, we must remember that the left side eigenvector matrix transpose is the inverse of the right side eigenvector matrix, right? So what happens then is what? That what makes a matrix have a large inverse? In other words, when will the inverse of a matrix be very large? When the condition number of the matrix is very large, right? Or, if you'd like to say it in another way, when two columns or two rows of this matrix are nearly linearly proportional, or if there are any columns or rows which are linearly, almost linear combinations of the others, then the matrix is poorly conditioned and its inverse will have large values. So what we conclude from this argument is that poor conditioning on phi, on the eigenvectors of the matrix, implies large values of the left side eigenvectors. Okay? Now, notice that the following happens. If you have that the eigenvalues, let's consider two situations. Let's say that this is one eigenvalue and this is another. Let's say this is lambda 1 and this is lambda 2. That eigenvalue lambda 1, let's say it's connected with an eigenvector phi 1. This eigenvalue lambda 2 is connected with an eigenvector phi 2. Now consider this other situation, lambda 1 and lambda 2. They are close. We call this the eigenvalue gap. Wait, I'm checking on the camera. Yeah. So we call that the eigenvalue gap. Now, this phi 1, lambda 1 comes with phi 1, this lambda 2 comes with phi 2. Now, granted, in a heuristic manner, we would expect that in this situation, the vectors phi 1 and phi 2, which corresponds to eigenvalues that are very close to each other, might start kind of looking alike also, right? Not necessarily, but they might. So if phi 1 and phi 2, which are here close, start looking alike, then that means that the matrix of eigenvectors will have two columns that are sort of close to each other, so the inverse is going to have high values, the left side eigenvectors will be large, and therefore this is a situation where we expect high derivatives. Right? We expect high derivatives because of the similarity between the eigenvectors. High derivatives in comparison to here where phi 2 and phi 1 have nothing to do with each other, they're far apart, right? They're less related, and therefore the conditioning of the right side eigenvectors is better and the left side is smaller. Now, I am not implying with this thing that one thing or the other is beneficial. I'm just bringing it up because later on in the class there will be some cases where we might be talking about the fact, maybe not, but it's in control theory, where we might want to affect the derivative of an eigenvalue. And in that case, we can see that if we want some eigenvalue to have large derivatives, we typically want to bring some other eigenvalue close to it. Okay? Now, I will leave that as is. And approach the next question, which is, what about the eigenvectors? Now, the eigenvalue derivative is a non-controversial issue, right? In other words, lambda j prime is equal to the left side transpose A prime times the right side. That is clean, clear, non-debatable, very well known, etc., and easy to understand physically. That means I change the parameter a little bit and this is what happens to the eigenvalue. But when you talk about the derivative of eigenvectors, the situation is a little bit less obvious because what? Because an eigenvector is just a shape, right? It's not like an eigenvalue, which is a number. So it's a shape. So when we talk about the derivative of the eigenvector, we might get some confusion arising due to what is the normalization of the eigenvector and so on, right? Now, that's not to say that we're not clear on what happens, but I'm just saying that the subject matter is prone to significant confusion. So let's look now at eigenvector derivatives. And for that, we take back to equation A. So I'll write again equation A, which was A prime phi j plus A phi j prime equals lambda j prime times phi j plus lambda j phi j prime, right? That was equation A. Now, before, when we were doing the derivation, I pre-multiplied by the transpose of the left side eigenvector, but in this case I am not going to do that. What I am going to do is take these two terms, put them together on this side as A minus the identity times lambda j multiplied by the derivative that I'm trying to find, and then put the other stuff on the right side, which is lambda j prime times phi j minus A prime times phi j. Minus A prime times phi j, right? Let's see, so what? Well, okay, so for simplicity of notation, let's just call this matrix Zj. Now, let's call this vector Bj. This vector Bj, we know what it is, right? Because we know the eigenvector, we know the derivative of the eigenvalue, we know the derivative of the matrix, we know the eigenvector. I could have written this thing as a, if I wanted to, I could also write it like this. I could say that it is equal to the identity times lambda j prime minus A prime times phi j, right? We could also do that. In any case, the important thing is that this is known and this matrix is known. And so what we have here is simply a linear system of equations that says Zj times what you want, which is phi j prime, is equal to Bj. Okay? Now, you would say, so what's the big deal then? That's it. Just solve for phi j prime. Okay? How would you solve for phi j prime? Well, you might think just invert Cj. But no, you can't invert Cj. Why? Because if you look at this matrix is rank deficient, right? Has a null space. Excuse me, I'm getting a call. I'm going to stop and then continue.